Okay, continuing on now. One thing to keep in mind about the first law of thermodynamics is that it's basically an accounting problem. You are trying to keep track of checks and balances here. You've got heat, you've got work, you've got a certain change of energy. The heat and the work together have to equal the change in energy, and so that's really all it is. So we saw that in this very simple example. Let's go to another example. This is a cyclic process. A cyclic process is a process where you start with a certain thermodynamic state and you end up back in the same state. It's kind of like if you're talking about gravitational energy, it's sort of like taking a round trip. Like if you're in a cross-country race, you start at the starting line and you finish back at the same place. But in the meantime, you go up hills and down through valleys, and you've increased your potential energy, you've decreased your potential energy, but you end up at the same place. It's a similar thing, but in this case with thermal potential. So here we have a PV diagram of a very simple cyclic process. It starts at A, it goes at constant pressure to B, okay. Then it cools off at constant volume to what's supposed to be C. This is mislabeled, so that's C. And then it goes across at constant pressure to D, okay, point D, and then it goes back to A. All right. So the whole point is that it has a certain thermodynamic state U that it begins at, and U initial ends up being the same as U final. Okay, so the first question is, how much work is done by the gas along path A, B, and C? Okay, so pause the recording here and try to figure this out. All right, hopefully you have realized that we're trying to do work here. We're figuring out the work done by the gas, okay, by, not on the gas, though it's the positive integral of PdV, and since it's a constant pressure process, you just merely multiply P times delta V. So you're really just figuring out the area underneath the initial pressure, actually all the way to the bottom here. Okay, so that is the work. And so it's 200,000 pascals times delta V is 3 cubic meters, and that ends up being 600,000 joules. Okay. Now, second question, how much work is done by the gas along path C, D, and A? Okay, pause the tape and try to figure out what it is. All right, well again, P dV, or P delta V, is your work done by the gas. But in this case, the delta V is negative. It's going from a large V to a small v, so it's a compression. So the work done by the gas is going to end up being negative. So it's 100,000 pascals times negative 3 cubic meters. And since it's negative 3 cubic meters, you end up with a negative 300,000 joules. So basically this area here underneath line CD is taken away from the work done by the gas. So the total work done by the gas is the shaded area inside the rectangle here. So what's happening then is that the gas is doing work, so it's losing energy. So whatever that gray area is, that's the energy that the gas had lost. But since it's coming back to the same internal energy that it started from, that has to be compensated by the heat. So the next question is, how much heat is added during the entire process? Okay, pause the recording and see if you can figure that out. Okay, again, we're coming back to the same internal energy. Okay, so your first law of thermodynamics is the change in energy is the heat plus the work on the gas. But in this case, the change in internal energy has to be 0. And so what that means is that the heat you add in this case is equal to the energy lost. It's equal to negative of the work done on the gas. Okay, so the work done on the gas is negative because the gas is doing the work. It's losing energy. That's the gray area, shaded area inside the square. And so that's the amount of heat you need to add to compensate. So it's plus the heat by the gas. And so that basically is 300,000 joules because the gas has lost a total of 300,000 joules. Okay, makes sense? Alrighty, let's go on. Now we're going to talk about a few special cases of thermal systems that we're going to be talking about a lot in the next few days and weeks. The first one is the easiest one. It's called an isolated system. We do not have to spend much time on an isolated system because an isolated system means nothing happens. It's a system where you can't do work and you can't put heat in and out because it's totally insulated, so nothing happens. Q is negative W equals 0 equals delta U. Forget about it. Not important. But we just have to mention what it is. Okay, a cyclic process we just talked about. Okay, a cyclic process can be much more complicated than this. Okay, for example, our process could have been like this. Okay, there could be an infinite number of ways. It could look like an amoeba. It could be infinite number of ways you can get from the starting point back to the starting point. But the point is, in every cyclic process, you start off with a U initial, you end off with the same U. The U final and U initial are the same. Starts and ends at the same thermodynamic state. Because of that, okay, it has the same initial PV and the same final PV, or the same initial N and T and the same final N and T. Okay, and that means that the internal energy change is 0, which means that the heat is equal to negative the work on the gas. Okay, so if the gas does work and loses energy, well, that's the amount of heat you have to gain. You have to put in. If work is done on the gas and it gains energy, well, that's the amount of heat you have to take away. Okay, so you have to make sure to compensate for the work by the heat, and that's all there is to it. Okay. An adiabatic process. Okay, an adiabatic process is a process where no heat is allowed to go in and out. It is totally insulated. Generally, an adiabatic process is a shallow curve on the PV diagram, kind of like this one here. Okay, it's insulated, and because of that, there's no heat exchange. So Q is 0, and since Q is 0, the only way you can change the internal energy is by work. So the only change in internal energy in going from U initial to U final is the work that the gas does. If it goes this way, the work is negative because it's expanding. If it goes this way, the work is positive because it's compressing. So it's all about the work. Okay, so the change in internal energy is all about the work in an adiabatic process. Okay, an isobaric process. Isobaric, if you've ever seen isobars on a weather map, you know that those are lines of constant pressure. Well, isobaric means constant pressure. It means pressure is constant, it does not change. And if you can just pause the video for a second, I would like you to try to draw a generic pressure volume diagram for an isobaric process. Give it a try. Okay, hopefully you came out with something like this, a horizontal line, because that is a constant pressure. Okay, we've already done sort of these in the cyclic process. We were working with constant pressures on the top and the bottom of the little box we drew. Okay. The nice thing about it is, and we've already used this, the nice thing about it is that you don't have to worry about using the P inside the integral. Because P is constant, you can bring it outside of the integral. So this P right here can be taken out, and therefore you have the integral of dV, which is just like the integral of dx. It's just the difference in V final and V initial. And so it's negative P delta V. So the work on the gas in an isobaric process is negative P delta V. Again, if delta V is positive, then it's positive work done by the gas and negative work on the gas. All right, and if delta V is negative. If it's a compression, then the work done on the gas will be positive. All right, isovolumetric, sometimes called an isochoric process, means a constant volume process. Okay, so take a moment, pause the video, and see if you can draw a generic isovolumetric process. Well, hopefully you came out with this. Okay, a vertical line. Okay, just like the sides of the box we did in the cyclic process. Okay, and basically the work is zero if there's no change in volume, and that means an isovolumetric process is all about the heat. Isovolumetric means the only way you change the internal energy is by the heat. So again, checks and balances. If you don't do one, you've got to do the other. In an adiabatic process up here, it's all about the work. In an isovolumetric process, it's all about the heat. And for other processes, it's a combination of both. Isothermal process. Okay, an isothermal process is just what it sounds like. Iso, again, means the same. Thermal means the same, in this case, temperature or thermal energy. So the temperature is constant, and that means that the internal energy, U sub T, is constant. U of T is constant. Now, the thing is, it's similar to a cyclic process, but you can have the same internal energy in different places along your PV diagram. Okay, because of course, remember, PV is proportional to T, right? PV is proportional to T, and therefore, if it's the same temperature, you can have different P's and V's, different combinations of P and V to give you the same temperature. For example, anywhere along this isotherm, this is considered an isotherm. You start with a certain P and V, you end with another P and V, but it's the same temperature, okay? Because, you know, PV is proportional to T, and so basically any P that's inversely proportional to V in this case gives you the same temperature. So U here is the same, U here is the same, U and temperature anywhere along this isotherm is exactly the same. Okay, and so it stays at the same temperature, and so basically whatever heat you add, you have to take it away in work. Whatever heat you subtract, you have to compensate by doing work on the gas. And so this should be W on. Okay, so the work is the inverse of the heat, and so again, checks and balances, you want to make sure nothing changes, and so that's how you end up with an isothermal process. The neat thing about an isothermal process and what makes it useful is you can do the work integral analytically, because you can figure out what P is. Okay, remember PV is NKT, and the nice thing is that means P is NK over V, and what we can do is we can take that and plug it in for P, and we end up with this integral here. The work on the gas in an adiabatic process is NKT over V times dV, from V initial to V final. The nice thing is N is constant, K is constant, and for an isothermal process, T is constant. So you can take all of this and bring it outside the integral, okay? And you end up with the integral of negative NKT times the integral of 1 over V dV. And hopefully you all remember that the integral of 1 over x dx is the natural log. And so we end up with this. W on is negative NKT times the natural log of the final volume over the initial volume. And that is a really, really useful relationship that we will be using a lot in the next few weeks. So you definitely want to write this one down. Okay, looks like we're almost at the end of our 15 allowed minutes. So we will wrap this one up. And that's pretty much the end of our first law of thermodynamics, formally anyway. We'll be still using it quite a bit in the days to come.